important. When I say Margules equations, these are the guys that I'm going to be referring to. Well, we may be a little bit unhappy with how good a straight line we got here. So we might try another way of doing the correlation. And here shows you all the results where I plotted out with the logs of the activity coefficients themselves. And you can see that it does, in fact, a pretty good job of predicting those activity coefficients. So the important curves that I'm looking at here are my log gamma 1 and my log gamma 2. But the others are plotted on here, just for completeness. Well, if we're unsatisfied with that fit, but we should be satisfied, that's very good. But if it weren't, we might try an alternative, and that is to plot not GE over RT x1, x2, but plot its reciprocal. Oops, too big. Namely this. And the constants that are thereby defined, if we get a straight line for that, are this way. It looks a little awkward, but that's the way it is done. So it's important to recognize that the constants A12 prime and A21 prime are different from the Margules constants A12 and A21. That's why the primes are there. Now if I put this together, what that gives me is an expression for the excess gives energy over RT that takes this form. So I'm in business to be able to extract from that, from the process that I had of differentiating NGE over RT with respect to N1 and N2 respectively, to get the expressions for log gamma 1 and log gamma 2. So that's perhaps a little awkward, but it might be worth an exercise to do it. This leads to the following. So I get these expressions now for log gamma 1 and log gamma 2 in terms of the constants A12 prime and A21 prime. You notice that now, if I plot it up, yeah, I get, looks like a slightly better straight line. It turns out it's insignificantly better. They're both have an R square of about 0.95. But the extrapolated limits here, the intercepts, give me 1 over their respective constants. This gives me 1 over A21 prime, gives me 1 over A12 prime. These are called the Van Laar equations. Now if I take the results that come out for A12 prime and A21 prime and plot up the resulting log gamma 1 and log gamma 2, you see it does an equally good job. So for this particular case, Van Laar and Margules did about the same job. That isn't always going to be the case. So if you try it out, so the process now is you've got the data set from VLE, you extract the log gamma 1, log gamma 2, you put them together in a excess gives energy function from which you can construct something that you can do linear regression on to get a straight line, giving you a 2 constant representation. And you can do it either as Margules does, and that is GE over RT x1, x2, or you can do the reciprocal and pull out what are called the Van Laar equations. And if one doesn't work very well, try the other one. It might work significantly better. But what we've got now are representations for the activity coefficients now in terms of 2 adjustable parameters that are used, are empirically fit from the data. Is everyone clear on the process that I've gone through here? And here again, I remind you that if the constants happen to be equal to each other, I already indicated that for Margules, we end back with the 2 suffix Margules equation and just a single constant. But here I can mention that the same thing happens if the Van Laar constants happen to be equal to each other. Obviously, then that's going to collapse into this same simple representation that I've indicated here. So very important, we've got these 2 representations for fitting activity coefficient information from VLE databases. And we have a simple procedure for doing it. The assumption here is in order to extract these constants, we need an entire data set to do it. But when we do that, what we find is the vast majority of systems are quite well fit by one or the other of these simple representations. So they're very important to know about. They have some limitations, and we can talk about, I'll be talking about that in due course. But for now, the important message is that these can do a good job for fitting data. So hope everyone is clear on how we would use these. Now these are also good if the system happens to have an azeotrope of either type. Then almost as often as not, we will have azeotropic behavior, particularly if the vapor pressures are fairly close to one another. So let's consider that. Turns out we can evaluate either Margules or Van Laar constants from azeotropic data. And there's a very, very large data set for azeotropes in the literature. Now, there's thousands of azeotrope points have been tabulated. And they can be either azeotropes at a given pressure or at a given temperature. By far the more common ones are atmospheric azeotropes, but you can find them of various kinds. But let's assume that we have knowledge of an azeotrope. The thing to appreciate is that knowledge of an azeotropic point is equivalent to two independent pieces of information that allow me to evaluate both a gamma 1 and a gamma 2 at the azeotrope. So we can write here for component 1 that gamma y1p is using, again, modified Rolle's law, and we're not going to deviate from that until for any further notice. So I can write out the equilibrium equations in terms of modified Rolle's law as follows, but if I'm at an azeotrope, then these two are equal, and I can just cancel them out. And at the azeotrope, the activity coefficient for component 1 is just the system pressure over the vapor pressure for component 1. And similarly for component 2, we can cancel out these mole fractions and extract the activity coefficient here as just P over the vapor pressure for component 2. So I've got from the data, because the data will provide for me, say, the total pressure, I've got an expression for gamma 1 and gamma 2. Well, using the Margules equations at the azeotrope, just writing them in here, these are now known quantities because I've got them here. I've got two equations and two unknowns. The unknowns here are A12 and A21, so I should be able to solve simultaneously for the two equations to extract expressions for A12 and A21. Everyone with me? So if I do that, this is the result. So I've written it here for you. So if we have knowledge of an azeotrope, then I can pull out the Margules constants here in terms of knowledge of the activity coefficients at the azeotrope. So these refer to conditions at the azeotrope. X1 and X2 are at the azeotrope. Of course, then the gammas are as well. Not at any other location. And if I do that, then I can pull out A12 and A2. Well, I should be able to do the same thing for the Van Laar equations. That's a bit of a bigger mess to solve the two simultaneous equations, but it can be done. And here is what that looks like. Well, A12 prime turns out to be log of gamma 1 at the azeotrope then. And here I've got expressions involving mole fractions at the azeotrope as well as the activity coefficients. Everybody with that? So if you were given an azeotrope, and I gave you a bunch of them yesterday, you should be able to come back and get either Van Laar and or the Margules constants that would describe that particular system. So look what that is. That tells us that if I have knowledge of the azeotrope all by itself, I can predict the whole behavior over the whole composition range. So we can think about that for a moment. That's going to be especially good if the azeotrope happens to be near the center of the composition range. If it's all over near one end or the other, such as the water ethanol azeotrope that we get, the maximum boiling azeotrope at 95%. Ethanol, that's not so good for predicting the whole behavior because we've got our azeotrope over at one end of the composition range. But if we're more or less near the middle of the range, this should be very good. And that's a powerful thing to be able to do. So, any discussion about this?
I had a quick
Yeah, you bet.
question that's adjacent to this whole lecture, kind of adjacent. Now that we're using the modified Raoult's law with the gammas, is this considered a modified version of the Lewis-Randall rule? Because I know we used the Lewis-Randall rule to derive the modified Raoult's law. So now we're still in that area where we have ideal gases and non-ideal solutions.
Yeah, it's a nomenclature question. So if you want to say if we want to call it a modified Lewis and Randall rule, that would not be wrong.
Okay.
But that isn't what people say. The language they use is modified Raoult's law. Yeah.
Does every solution have an azeotrope?
Does every have what?
An azeotrope?
No. So if you didn't have an azeotrope, you can't do this. But a lot of them do have azeotropes. So when you do, then you can do this. And it's a very powerful tool to be able to use. Well, sometime earlier I made the assertion that there are a number of reasons for it, but the preponderance of attention that investigators have given to systems like this are around binary systems. And I made the assertion that, well, maybe that's justified technically because it turns out that we can predict from binary data, if we know how each of the, let's say I have a solution of A, B, and C, if I know how a solution AB behaves, and AC behaves, and BC behaves, I should be able to put that binary information together in order to construct a description of the ternary solution. And the reason that makes sense is that binary interactions, even in liquids, are far more prevalent than any other higher multi-body interactions. So it makes some physical sense, so we should be able to do that. Well, now we have a way of taking a closer look at that possibility. So let's consider extension to 3 or more components using binary data. Well, I can do it in terms of the excess Gibbs energy. So if this is the excess Gibbs energy, let's say, for a ternary, I can maybe put a subscript 1, 2, 3 on that. Turns out I can write it as the sum of the corresponding binary interactions that exist in that ternary solution. So I have an excess Gibbs energy for the binary 1, 2, and for the binary 1, 3, and the binary 2, 3. And the total interaction in the ternary solution can be just put together as the sum of those 3 binary interactions. So let's see how that plays itself out here. And obviously it gets a little bit, deep, get into the weeds a little bit here. But if we have this simple representation, so the excess Gibbs energy for the binary interactions are all describable by what I've called the 2-suffix Margules equation, that is just involving a single constant. Then I might call that constant, if it's 1, 2 here, I could call that constant 1, 2, like this. And if that representation is good enough for all 3 of the binaries, then putting it together in this form results in something that isn't too hairy. You just get this representation, the sum of these 3 terms. And so I think you could imagine extracting the activity coefficients log gamma 1, log gamma 2, log gamma 3 out of this using the same mechanism that we had before, that is differentiating the extensive form of this with respect to the different mole numbers. Well, if it's Margules, then it would look like this. It's easy enough to write it down. So now what I've got are all these binary pair constants, 1, 2, and 2, 1, but then I've got 1, 3, and 3, 1, and 3, 2, and 2, 3. So again, I could extract from that expressions for an activity coefficient of any one of those ternary components. And it's also evident that if I had more than 3, I could just add more and more terms, whatever is going to be needed. Van Laar looks like this, just adding up the 3 contributors to GE. And then I'm making the statement here that the various log gammas can be extracted by the same mechanism as I did before. Now, let's say that we've done this, we studied a particular set of data. We've extracted constants that are enough to be able to describe these systems, and our main focus is, of course, going to be on binary systems here. But it's important that you realize that this is true. But if I had systems that are binary or any number of components, and I had prior knowledge of the activity coefficients as a function of composition, so let's assume now that I've got that. Now I can go back to all of those kinds of problems that I solved for Raoult's law with knowledge of activity coefficients. See what I'm saying? So we could be able to go back and calculate bubble point pressure, bubble point temperature, dew point pressure, dew point temperature now, but we've now got to include activity coefficients in these, so we're using modified Raoult's law instead of Raoult's law itself. And the systematic way to do that I've outlined here. And what you'll notice is when you go through this, and I've got the whole thing here for you, it takes 2 pages to write it all out. But this is a reconstruction of the same thing that I already had provided for you when Raoult's law is valid. But now when we've got activity coefficients, they are functions of the liquid composition, and it adds an additional wrinkle. Because now what you have to do is you don't know those going in. Because you may not, when you don't know the liquid composition, you don't know the activity coefficients. And so they have to be part of your iteration. So what we've got here, look at this problem. If I'm given the vapor phase composition and the temperature, and I'm asked to calculate the dew point pressure and liquid phase composition, before that could be done without any ado. You had no iteration or anything, you could just go and solve it. But now what I have to do is realize that gammas here depend on this unknown liquid composition. So I have to start out by assuming all the gammas are 1. And that gets me going on the iterative scheme for this. I'll calculate pressure from the above equation, and then all the xi from that. In Raoult's law case, you were done at that point. But now that gives us a set of x's from which we can calculate a new set of gammas, put them back in and do it again and iterate that to convergence. If the liquid composition is known, then that's not a problem. So if I'm given that, then it's fairly straightforward, but I have to do an iteration if I have to determine temperature, because that is buried in my Antoine equations. The worst case of all is this last one, where you're given the vapor composition and the pressure, and you need to calculate the dew point temperature and this liquid composition. So now the iterative scheme involves a few more steps, because the unknown gammas associated with the unknown liquid compositions are involved. But once you set up the spreadsheet for this, then it's sort of a piece of cake. You just have to pull down and it will converge just like you did before. So this is actually where I want to end today, because we're going to start discussing the weaknesses of Van Laar and Margules. Discuss that tomorrow, and then what we can do about that, and what the status of the current situation is with respect to describing non-ideal vapor liquid